Howdy, we are the Stallions group, and I'm Fidel. My team members are Tuan, Steven, and Samir. And today we're going to talk about our project, which is Temporal Thermal Convert Channel in Cloud FPGAs. This project is based on the paper of the same title from two students from Yale University. With the increasing interest in cloud FPGAs, it is inevitable that it becomes more and more of a target for information leakages and any other data issues. The current business model of cloud FPGAs right now focuses on temporal sharing, which is someone can use the same FPGA when someone else is not. And it also has delved into spatial sharing, which is multiple users using the same FPGA at the same exact time. The method we are exploring right now, the temporal thermal convert channel, has not been widely explored, and it's one that does not require either. In this project, we will implement a ring oscillator sensor and a counter to mimic a temperature sensor, which is able to obtain information from the heat generated by the previous user of the FPGA.
Okay, so for our project, we started the implementation with the diagram or template, as you can see. Uh, for the ring oscillator, we used a generate block consisting of an AND gate and 75 inverters, uh, as well as a counter, a 20-bit counter. And then using the ring oscillator, we were able to use a communication logic and connect it to the controller, the Zybo board. Um, and For the generate block, we use 75 inverters specifically to create a large amount of inverters that create increase in temperature so that we can examine it later on the Zybo board. And the 20-bit counter is used to just keep track of the oscillations of the signals from low to high. And To monitor these temperatures, we are simply using the LED lights on the Zybo board.
Okay, so this is our ring oscillator Verilog code. So as you can see, we established our parameter, which is the amount of inverters. We have our inputs established, outputs, and then as you move down, you see this is where our generate function is, which is basically a for loop, which goes to the inverters. And then all these codes that we have commented out were we were supposed to use to implement on the FPGA, but we never ended up getting to that part. And then for our counter file or source file, here's the code for that. This is a 20-bit counter. And the always statement right here mentions that whenever there's a positive edge on the input signal, basically when it goes from 0 to 1, it's going to run through these if and else statements. If the reset is a 0, it's going to output 0. And then if the reset is not 0, then it's going to keep adding to the counter.
Okay. So to test these source files, we use this ring oscillator test bench. It's a pretty standard test bench. We have our wires and registers. Here we get the register from the counter. This is associated with the the counter as well. This is actually associated with the oscillator. This is associated with the counter. This is going to be the output of the counter, and this is the output of the oscillator. And so here we instantiate both the ring oscillator and counter. First, we have the ring oscillator perform its oscillations, and the output of that would be going into the counter, where we would be counting those oscillations. And here we monitor the results. And here we stimulate our sources and use delays to help see those results in the waveform. So let me just show that. So here we have our results. And as you can see, we have these red parts coming from the oscillator output, and these are unknown values, basically due to the unnatural nature of the ring oscillator feeding back into itself in Verilog. It's causing these unknown values. However, the output of the counter is still registering them as low to highs, which is exactly what we expected. And the counter, as you can see, is working on every positive edge. Here it's 3, 4, and so on. Now, after we have tested our source files, we attempted to connect our program to the FPGA, and this is where the XDC file comes in. We have our package pin. This is associated with the physical location of the components on the FPGA board, and these are our variables from our source files. In conclusion, we were only able to implement the receiver side of the covert channel communication due to hardware issues and not being able to fully implement this on the FPGA. We weren't able to get to the sender side of the communication of the covert thermal channels.